Hello, differential equations. Right now, today is March 30th, and we're doing activity 321 from section 3.2. So in this activity, we're dealing with planar systems, meaning that they are linear and only two-dimensional, so they fit in the plane. And we've got here a linear system with coefficients 23, 10, negative 15, negative 22. So what this means is that you've got x prime, mark it there, x prime equals 23x plus 10y, and y prime equals negative 50x minus 22y. That's what that coefficient matrix means. And we know that x of 0 equals 3 and y of 0 equals 3. That's what we mean by the boldface x of 0 being 3, 3. Okay, so now we need to find the eigenvalues and eigenvectors of this matrix. So 23 minus lambda, and then 10, and then negative 50, and then negative 22 minus lambda. We'd like to determine that, set it equal to 0. Let's see what we get. These numbers are big. This could be fun. All right, so 23 minus lambda times negative 22 minus lambda minus a negative 500, so plus 500 equals 0. Okay, so the negative lambdas I'll do first. Lambda squared. And then the linear part of the lambdas. So I've got negative 23 lambda and positive 22 lambda, so there's minus lambda. And then 23 times negative 22, 23 times 22 negative plus 500 is negative 6. Okay. Well, let's factor that. That's lambda minus 3 times lambda plus 2 equals 0. We have lambda equals 3 and lambda equals negative 2. Okay. Then, so for lambda equals 3, we've got 23 minus 3, 10, negative 50, negative 22 minus 3 times xy equals 0, 0. Didn't really fit there very well. Too much spacing, oh well. So that means that I've got 20, 10, negative 50, negative 25 times xy equals 0, 0. Of course, these are the same equation, just different by a scalar. So my favorite equation is really the top one, but I can divide that by 10 and it's still the same equation. Because 20x plus 10y equals 0, divide both sides by 10, and you get 2x plus y equals 0. So y equals negative 2x. And so then if x is 1, y is negative 2. That means the eigenvector is 1, negative 2. Okay, let's do the other one. 23 minus negative 2, and then 10, and then negative 50, and then negative 22 minus negative 2 times xy equals 0, 0. Can't really fit that, my last parenthesis in there. All right, and so then you've got 25, 10, negative 50, negative 20 times xy equals 0, 0. So then my favorite one is one of the positive numbers. I can divide it by 5. So 5x plus 2y equals 0. So x could be 2, y could be -5, and that's 1. There's an infinite number of solutions for this because it's basically like a line. But one of the nicer solutions is when x is 2 and y is -5. Okay, so those are our eigenvectors and eigenvalues. Now we want to find straight line solutions for this and plot them. And then we want to sketch the initial. So let's see. I should move to Desmos. Perhaps I will. Okay. Let's move to Desmos. My screen is too big. Let's get a little smaller so I can see here. Okay. Now, by the way, when you guys are, if you're doing your homework in Desmos, you should be share graph, export image, and then copy it into a Word document or whatever else you're doing. Please don't have a Word document with a link to the Desmos. That's wastes me a lot of time. All right. Nobody got time for that. So we're going to sketch these graphs. So the vector 1, -2. Think about like the 1, -2. So t, -2t from, let's say, -10 to 10, and 2t, -5t, say -5 to 5. That's one way to do it. The other way to do it would be to say, well, to go through, wow, this is so close together. The other way to do it is to say, well, if you're going through 1, -2, then your slope is -2. So then instead of doing that, you could just do y equals -2x, which is actually how you solve that equation. So yeah, and then in here, the last equation we had was 5x plus 2y equals 0. You do that one, or you just solve for the y. So y equals -5 over 2x. Okay, so those are the solution. So those are straight line solutions for this differential equation. Now let's sketch the curve of the initial value problem. I'm going to come back to that because we'll see that I can find an analytic solution to that. So here, I've got, now notice, by the way, that this red line corresponds to an eigenvalue of 3, which would be going further away. And the blue line corresponds to an eigenvalue of -2, which would be going towards the origin. Okay, now we're going to show that C1 e to the lambda t v1 plus C2 e to the mu t e2 is the solution to the linear system. Okay, so how do we want to show this? That way for now. Let's see. Okay, so recall that A equals 23, 10, -15, -22. We found lambda equals 3, corresponding to V equals, I guess, what, V1. Call it V1, the same as the book. Corresponding to V1 being the vector 1, -2. And we found, we'll call our second eigenvalue mu, kind of like they are. That's -2. And B2 is 2, -5. Okay, so x of t equals c1 and then e to the 3t e to lambda t times 1 -2 plus c2 times e to the -2t times 2 -5. Is this a solution to the differential equation? Well, let's see. So a times x is going to be equal to so I should write x as a vector. So x of t as a vector then is going to be something like c1 e to the 3t plus 2 c2 e to the -2t and then -2 c1 e to the 3t minus 5 c2 e to the -2t. Okay, so that's really as in a whole vector. And so then a times x, so a does row times column. So row times column would be 23 times that plus 10 times that. So our e to the 3t will stay the same. And so you'll get a 23 times this plus 10 times that. So 23 C1 E, no. 23 C1 minus 10 times the other one, 20 C1. Oh, come on. Arithmetic. So then AX equals, well, they both got C1 there. And so 23 times that minus 10 times that will be 23 minus 20. So 3 C1 e to the 3t plus, and then here, that'll be 23 times this plus 10 times that. So 2 times 23 is 26 minus 50 will be, well, yeah, 46 minus 50 will be plus or minus 4 C2 e to the -2t. And then the bottom, we're doing the bottom row times these two. So then -50 times this minus 22 times that. It's going to be -50 plus 44. So minus 6 C1 e to the 3t. And then this here would be -50 times that plus 22 times that. So -50 times that is -100. 5 times 22 would be plus 110. So plus 10 C2 e to the -2t. Okay, so let's write this as, again, being basically C1 e to the 3t times the vector 3 -6 plus C2 e to the -2t times -4, 10. And really, I could have just had the matrix multiply times that vector and that vector. Sorry, you can't see the matrix. Should have had the matrix just multiply times that vector and times that vector. And that would be simpler. That's kind of what I was doing already, simplifying. So the way I should have done this, that would have been simpler, would just to take the matrix times the vector 1, negative 2. So the matrix times the vector 1, negative 2. 23 minus 20 is 3. So boom. And then negative 50 times 1. Negative 50 times 1 minus, so plus 44, so negative 6. Boom. And then the other two there. Because these, you can't see that. Because the C1s, the C2s, the E's, the powers, those are constants. So they kind of move through. And you can just do the matrix times the coefficient vectors there. And so this just feels so much nicer than that, as far as like looking simpler. All right, well then, how does that compare to x prime of t? Well, x prime of t is take your original x of t here, and you take the derivative, everything's constant except the e to the 3t and e to the negative 2t. So you get a factor of 3 there and a factor of negative 2 there. Well, that's also c1 e to the 3t times 3 negative 6 plus c2 e to the negative 2t times negative 4, 10. Because you're getting a factor of 3 there and a factor of negative 2 there. So, checks out. So ax equals x prime of t. So that is a solution. Okay. All right, now use the fact that x of 0 equals 1/2 to find c1, c2. Wait, x of 0 equals 3, 3. Find c1, c2. Oh, I should have solved for c1 and c2. That'd be even nicer. So some sort of typo going on here. I'll use the original 3, 3. I'm confused why x of 0 is 3, 3 and x of 0 is 1, 2. All right, let's use the original. X of 0 is 3, 3. So then x of 0 equals, so the original x was basically, so 1, negative 2, plus, or c1, 1, 2, plus c2, 2, negative 5. That's equal to c1 plus 2c2 and negative 2c1 minus 5c2. Okay, so this is supposed to be equal to 3, 3 originally. So then basically we're kind of doing some, you want to put like, basically doing reduced echelon form here. And so if you're, say, on Sage, you just do that. Or you can solve it algebraically. Let's show you how to solve it on Sage. So I'm starting up Sage now. And that's kind of overkill to use Sage on a 2x3 matrix. But I think it's also good to show you how to do it, because if we ever get into some bigger applications, it'll be really useful. So equations. Let's have a new worksheet. Okay. So here you have A equals, we'll kind of append the 3, 3 to the end. So it's going to be matrix, and the original matrix was, well, our coefficient matrix is basically 1, 2, 3, negative 2, negative 5, 3. Okay. What did I do wrong? Okay. How about show A? Okay. So then 1, 2, so these are that's the vector for C1, that's the vector for C2, then 3, 3 is what it needs to be when you plug in 0, 0. Now, if you just do show a dot rref, if you can't remember commands, you press type tab, and it completes the commands for you there. Complete. So that means C1 is 21 and C2 is negative 9. So so I could solve this algebraically and get C1 equals, I can't remember. 21 and negative 9. 1, 2 equals negative 9. So then with our Desmos graph, we could plug that in here. So where did that go? So let's do y equals e, let's see, 21 times e to the 3t. Let's call, we're graphing with respect to x. Let's do 3x times times the vector, here's the deal, because I've got an x and a y here, put your x before the comma and your y after the comma. So then your x terms are all on the top. So x is c1 e to the 2t times the vector 1, 2, so we're doing the top first. So 21 times e to the 3t, then minus 9, 2 times 9, this is the top, 2 times 9, so 18, e to the negative 2t, comma, and then c1 is 21, so negative 2, so negative 41, and 42, e to the 3t, and then minus, and c2 is 9, so negative 5 and negative 9 is plus 45, e to the negative 2t, good. All right, so we're starting off there, and it basically goes starting off at 3, 3, and it shoots down. Okay. Let's solve for the other example, where it was instead of being 3, 3, it was instead of being 3, 3, we could do it 1, 2. So instead of 3, 3, got 1 and 2. Well, that matrix B. And then show RAF. C1 is 9 and negative 4 instead. So if it was 9 and negative 4 instead, we could be graphing from 1, 2. So then do, let's see. So instead of 21, we're doing 9. So we'll just kind of do this. And take these numbers. So that's numbers, and that's the 21 is 9. So negative 2 times 9 is negative 18. And then a 9 there. And then instead of a negative 4 here, so negative 2 times 4 is 8. And then negative 5 times negative 4 would be 20. So that starts from 1, 2. So that goes that way. Okay, so now we've graphed the other initial condition. And that completes this activity.